Welcome to our nocturnal laboratory of gentle discoveries. Here at Dreamtime Science, we transform complex concepts into lullabies for the curious mind. You know, I've been thinking about something that feels both huge and quietly mysterious. What if the rules that govern everything around us aren't as fixed as we usually believe? There's something remarkable about imagining that the physical laws, the very fabric of how the universe works, might have shifted ever so slightly over time. It's a gentle reminder that even the most familiar parts of our world might hold surprises, and I can't wait to share what that could mean with you tonight. If you find peace in these nocturnal discoveries, consider becoming a regular visitor to our quiet corner of science. Share in the comments what topic you'd love to dream about next. Now, take a moment. Adjust your blanket. Find the perfect hollow in your pillow. Let your shoulders melt. Breathe in and out. There is a certain hush that settles over the world in the late hours, when the sky is deep and the stars begin to pulse with ancient, silent wisdom. It is in this nocturnal quiet that the mind finds itself most inclined to ponder the hidden frameworks that bind the universe. Above us, the constellations march along their predictable paths, each star obeying rules set long before any mind could give them names. Beneath us, atoms vibrate in the darkness, as unyielding in their obedience to law as the celestial bodies themselves. It is as if, from the very first moment of existence, the cosmos was issued a set of instructions, immutable, elegant, and mysterious, around which all things must dance. These are the physical laws, the constants of the cosmos. Their names are whispered in classrooms and laboratories, but they are also the silent companions of dreamers and storytellers, those who look up and wonder, what if? What if these laws could be broken, or bent, or simply turned aside for a moment, like the rules of a game? Science fiction, that great theatre of speculative thought, is forever pushing at the boundaries of these laws, turning them over and over like stones in a river, searching for hidden chambers of possibility. But before one can imagine a world where the speed of light is not a limit, or where time flows backward like a receding tide, one must first understand the profound regularity that underpins our own universe. The very idea of a law of nature is itself a kind of poetry, a recognition that amidst chaos there is order, a code written not by hand but by the structure of reality itself. Consider for a moment the speed of light. In the early years of the 20th century, a young patent clerk named Albert Einstein looked past the flickering gaslights of his office and asked a question so simple it was almost childlike. What would it be like to chase after a beam of light? From this playful curiosity, a revolution was born. Einstein's theory of special relativity, published in 1905, would forever change how we see the fabric of space and time. The speed of light, 299,792,458 meters per second, a number that hums with precision, became not just a fact, but a boundary, a fence marking the edge of what is possible. Light, in the universe as we know it, is swift beyond comprehension. If you were to switch on a torch, the photons would race away from you at that immutable speed, crossing the breadth of the earth in a fraction of a second. Yet no matter how fast you run behind them, those photons remain just as far ahead. It is as if the universe conspires to keep light, the ultimate sprinter, always outpacing even the most determined pursuer. This speed limit is woven into the very equations that govern reality. It is more than just a property of light. It is a statement about causality, about the sequence of events, about the very possibility of cause and effect. Were it not for this limit, paradoxes would proliferate. Effects could precede causes, information could escape black holes unchecked, and the arrow of time itself might lose its meaning. In the hands of a storyteller, this law becomes the seed of wonder and despair alike. In Christopher Nolan's film Interstellar, The speed of light is not merely a number, but a wall that separates the desperate astronauts from their families on Earth. Each moment spent near the gravity of a black hole stretches time so that hours become years. The laws of relativity are not just background, they are the very engine of the plot, shaping destinies and breaking hearts. The film's haunting chronicle of separation and return is a meditation on the limits imposed by the cosmos and the human yearning to transcend them. Yet even as we contemplate the speed of light, there are other laws, older and perhaps even more inscrutable, that govern the fate of all things. The laws of thermodynamics are among the most unyielding, the ancient edicts that command the flow of energy and the direction of time. The first law is an assertion of permanence. Energy cannot be created or destroyed, only transformed. This is the universe's promise that nothing is ever truly lost. Energy merely changes its mask, shifting from the blaze of a star to the warmth of your skin, from the whirring of a machine to the silence of cooling metal. In every interaction, in every breath, the balance is kept. But the second law is more somber, a whisper of entropy that haunts every act of creation. Order always gives way to disorder. Heat flows from hot to cold, not the other way around. In any closed system, the total entropy, a measure of randomness, of chaos, can only increase. This is why a cup of tea cools on a winter's night, why stars eventually burn out, why memories fade. The universe is a grand procession from order to disorder, a slow descent into equilibrium. H.G. Wells captured this melancholy in his novella The Time Machine, where the traveller moves forward to a distant age and finds the sun grown dim, the earth cold and silent, its once vibrant surface reduced to dust and twilight. The story is a vision of thermodynamic fate, a world where the second law has played out to its ultimate conclusion. And yet there is a strange comfort in these laws, for they are also the predicates of all structure and possibility. Without the first law, the world would flicker in and out of existence, a ghostly chaos without pattern. Without the second, there would be no flow of time, no seasons, no birth or decay, merely a static tableau, frozen and unchanging. Science fiction writers have often wondered, what if we could cheat these laws, even for a moment? What if we could travel faster than light, leap across the galaxy in the blink of an eye? What if we could reverse entropy, restore the broken, the lost, the dead? These dreams are not just escapism, they are a tribute to the power of the laws themselves, for only something unbreakable is worthy of such longing. In Isaac Asimov's short story, The Last Question, humanity's greatest minds ask again and again whether the heat death of the universe can be averted, whether entropy can be reversed. The answer is always the same, until at last, in the farthest future, the universe's last spark flickers, and the question is answered in a way both poetic and profound. The story is a meditation on the tension between law and hope, on the yearning to transcend even the most fundamental of constraints. It is not only in fiction, though, that the constants of the cosmos inspire awe. In the laboratory, the laws are tested again and again, their universality confirmed in the fall of an apple, in the flicker of a flame, in the motion of distant galaxies. The constants, Planck's constant, the gravitational constant, the fine structure constant, are measured with ever greater precision, their values written into the very operation of the instruments that measure them. The universe seems to whisper the same numbers, the same ratios, wherever we look. Imagine a world where these constants were different, a universe where the electromagnetic force was stronger or gravity weaker. The stars might burn out in moments or never ignite at all. Chemistry would be unrecognizable. The very fabric of matter might never coalesce. The anthropic principle, that curious philosophical notion, suggests that we observe these constants because they permit the existence of observers like ourselves. In the multiverse of science fiction, each universe is a roll of the cosmic dice, Only in a rare few do the laws align to permit the emergence of life and of minds that can wonder at their fortune. In every civilization there comes a time when myth and measurement meet. The Greeks spoke of the music of the spheres, the harmonious motions of the planets, as if the universe were a kind of cosmic lyre plucked by unseen hands. Today we know that these harmonies are the result of gravity's law, first articulated by Isaac Newton, who saw in the falling apple the same force that binds the moon to the earth. Newton's law of universal gravitation was a revelation, a single equation that could describe the orbits of the planets and the motions of apples alike. It was, as Newton himself wrote, thinking God's thoughts after him, a discovery of the hidden architecture that holds the world together. Yet Newton's laws, precise though they are, were only the beginning. With the rise of quantum mechanics and relativity, the universe was revealed to be far stranger than any clockwork. Particles exist in states of possibility, not certainty. Time and space themselves are woven together in a fabric that can bend and stretch. The laws remain, but their meaning is subtler, more elusive. They are no longer simple edicts, but symphonies of probability and geometry. It is this very strangeness that fuels the imagination of those who write and read science fiction. In Ursula K. Le Guin's The Dispossessed, the laws of physics are not just constraints, but keys to new kinds of freedom and community. In Liu Cixin's The Three-Body Problem, the very nature of physical law becomes a battleground, as alien civilizations seek to rewrite the rules themselves. Each story is a meditation on what it means to be bound, and what it means to dream of escape. Yet, as we close our eyes and drift towards sleep, there is a deeper magic in the simple fact that these laws exist at all. The universe could have been chaos, a featureless void without pattern or memory. Instead, we find ourselves in a world of rhythms and cycles, of rising suns and falling apples, of stars that burn for billions of years. The laws are not chains, but the scaffolding on which all beauty is built. And so, in the darkness, as the stars wheel overhead and the night air grows still, it is perhaps worth lingering for a while among these constants. We are their children, their inheritors and their questioners, living out our brief lives in the interval between order and disorder, certainty and possibility. The stories we tell, of faster-than-light travel, of time machines, of worlds where entropy can be undone, are testaments not only to our imagination, but to our reverence for the mysterious regularity that shapes our every moment. The night is long, and the laws of physics remain, patient and silent, awaiting the next question, the next dream, the next leap into the unknown. As the gentle tick of entropy continues, as photons rush away at the speed of light, a new inquiry stirs in the mind, shimmering just beyond the reach of certainty. What deeper symmetries might yet be found? What hidden principles might underlie the laws we know? The journey of discovery unfolds, unending, through the quiet corridors of the cosmos. The universe, in all its grandeur, lulls us into a sense of constancy. We gaze up year after year, and the constellations seem fixed in their silent procession. The same stars glow with familiar light, the same moon ascends, and the same planets wheel across the midnight stage. Beneath this canopy, the rhythms of nature, of seasons, tides and orbits, repeat with a regularity so profound it feels as if the cosmos itself is governed by a code both eternal and unyielding. The laws of physics, so we are taught, are the ultimate invariants, pillars upon which all that is and all that will ever be are built. Yet, as we drift deeper into the hush of night, let us loosen our grip on certainty. Let us wander into the notion that the universe, far from being a fortress of immutable rules, may be a place of evolving laws, of inconstancy at the most fundamental level. In the quiet shadows, questions take shape. What if the laws of nature have not always been as we now measure them? What if the universe, in its infancy, played by rules subtly or even dramatically different from those we observe today? To approach these mysteries, we must first peer into the heart of the cosmos itself, into the story of its beginnings. The Big Bang, that primal eruption from a singularity, a point of unimaginable density and heat, is not so much an explosion in space, but rather an explosion of space, of time, of all the quantum fields that would one day coalesce into matter and light. Here, in this crucible, the universe was not merely born, it was defined. In the prevailing narrative of modern cosmology, the laws that govern energy and matter, space and time are regarded as fixed. The constants of nature, the speed of light, the gravitational constant, the charge of the electron, are the same everywhere and everywhen. This assumption runs deep, threading through every equation, every prediction, every explanation for how stars shine, why atoms hold together, and how galaxies form. But does this immutability hold even at the universe's dawn? The evidence we possess is indirect, filtered through the haze of eons and the veil of cosmic expansion. What if, in those first trembling instants, the laws themselves were in flux? Consider the constant most sacred to physics, the speed of light in a vacuum, denoted as k. It is an almost mystical number, 299,792,458 meters per second, a cosmic speed limit, the ultimate barrier for information and causality. Yet, in the speculative corridors of theoretical physics, some have dared to imagine a universe where Hsu was not always what it is now. The idea of a variable speed of light is both audacious and strangely compelling. In the earliest moments of the universe, perhaps the speed of light was vastly greater. If so, the consequences would ripple outward, altering the very fabric of cosmic history. The horizon problem, which asks why regions of the universe separated by great distances appear so similar, finds a new answer. If light, and thus information, once travelled much faster, then distant parts of the cosmos could have equilibrated before slowing to the present pace. This is not mere conjecture, it is an attempt to address genuine puzzles. The smoothness of the cosmic microwave background, the afterglow of the Big Bang, is difficult to explain if information could never have traversed the vast distances we now see. Inflationary cosmology, the standard solution, posits a brief period of exponential expansion, stretching minute regions into cosmic enormity. But a variable speed of light offers another possibility. Perhaps the limits themselves were looser, the boundaries more forgiving. Let us pause, then, at the threshold of such speculation. What does it mean, philosophically and scientifically, to suggest that the laws of nature can change? We are accustomed to thinking of science as the search for eternal truths, laws carved into the bedrock of reality. If these laws themselves are mutable, then what is left to discover? What becomes of the very notion of a law, if it is but a chapter in a longer narrative? Some physicists argue that a changing law is not, strictly speaking, a law at all, but rather a contingent rule, a local custom of the universe, valid only for a time or a place. The implication is profound. Our equations may be akin to dialects, intelligible only within a particular epoch, destined to evolve as the cosmos unfurls. The suspicion that physical laws might be variable is not entirely modern. In the late 1930s, Paul Dirac, one of the titans of quantum theory, wondered aloud whether the constants of nature might be connected to the age of the universe. He noticed that certain large numbers, derived from ratios of fundamental constants, were eerily close to the number of seconds since the Big Bang. Was this coincidence? Or was there a deeper connection, one that hinted at evolving laws? Dirac's large number hypothesis suggested that the gravitational constant, g, might slowly change as the universe ages. Though subsequent experiments have placed strict limits on how fast such changes could occur, the idea lingers. Perhaps not all constants are as constant as we believe. Quantum mechanics, too, whispers of inconstancy. At the smallest scales, the universe is a flickering tapestry where probabilities reign and uncertainty is fundamental. The vacuum itself seethes with virtual particles, popping into and out of existence, lending a restless dynamism to what we once thought of as empty space. The so-called fine structure constant, which governs the strength of electromagnetic interactions, is a dimensionless number, a pure ratio, immune to shifts of units. Yet some astronomers have searched for evidence that this constant, too, may have changed over cosmic time by analyzing the light from distant quasars, whose journeys span billions of years. The evidence is, at best, ambiguous. Measurements are difficult, the signals faint and susceptible to subtle errors. But the possibility remains. The laws we know may be but one stanza in an endless cosmic poem, their verses subtly rewritten as the universe matures. If the physical constants can change, then the very story of the universe might be far stranger than we imagine. Stars, for example, derive their luminosity from the balance between gravity and nuclear fusion. If gravity were stronger or weaker in the past, the lives and deaths of stars would unfold differently. The formation of galaxies, the synthesis of elements in the crucibles of stars and supernovae, even the chemistry of life itself, all are delicately tuned to the values of these constants. A variable speed of light, in particular, would reverberate across the great epochs of cosmic history. Cosmologists have constructed models in which Pantsu was far larger just after the Big Bang, shrinking to its present value over time. In these models, the early universe would appear dramatically different through the lens of physics. Horizons would be larger, the causal structure of space-time transformed. This is not a proposal without controversy. For the laws of physics to change, something must govern the change, a meta-rule, a higher-order law. If Q can vary, then what determines its variation? Is there a deeper principle, still hidden from our understanding, that writes the rules for the rules themselves? Some have speculated that the laws of physics are environmental, shaped by the conditions of the universe at a given time. Others suggest that the universe is but one of many, each with its own set of laws, an idea known as the multiverse. In such a vision, the constants we measure are local facts, the result of cosmic lottery, with different pocket universes playing by different codes. The so-called anthropic principle enters here. Perhaps we find ourselves in a universe with life-permitting laws simply because only in such a universe could beings like us arise to contemplate them. The philosophical implications are dizzying. If the laws of physics can change, or if there are many sets of laws across a multiverse, then the search for ultimate explanation becomes more elusive. Science would shift from uncovering necessity to exploring contingency, a tapestry without a single unbroken thread. Yet, for all the grandeur of these possibilities, we must return to the evidence. The cosmic microwave background, the afterglow of the Big Bang, is a relic from when the universe was just 380,000 years old. Its uniformity, its minute fluctuations, are a testing ground for theories of changing laws. So far, the measurements are consistent with the constants we know, but the door remains open, ever so slightly, to new physics. In the quantum realm, uncertainty reigns. The vacuum is not empty, but alive with possibility. If the laws of nature are the rules governing this restless dance, could they themselves be subject to quantum indeterminacy? Some physicists have speculated about quantum gravity, a domain where the geometry of space-time itself is quantized, where the laws may shimmer and shift at the smallest scales. Here, perhaps, the notion of constancy is replaced by probability, by a cosmic dice roll, at the dawn of time. As we drift through these speculations, the night deepens. The stars overhead, so constant to the naked eye, are revealed as beacons from a tumultuous past, each photon a messenger from ages when the universe was younger, hotter, perhaps governed by different rules. In the silence, we are left with a sense of both humility and wonder. The laws of nature, once thought eternal, may be as transient as the patterns of clouds, as mutable as the tides. The universe itself may be in the midst of an unfolding story, its rules not fixed, but written as it goes. Yet the mystery only grows richer. If the laws can change, what guides their evolution? Are we poised at a moment of unusual stability, or is change the true constant? The light from distant galaxies carries not only the story of matter and energy, but perhaps also the tale of laws in flux, a cosmic palimpsest overwritten with each passing age. As you close your eyes, let the questions linger. The constancy you feel is but one layer of the universe's song. Beneath it, deeper harmonies may yet be discovered, notes of inconstancy, of laws in motion, of a cosmos still finding its own voice. The journey is far from over, and the night's inquiry stretches onward into realms where the very meaning of law and order dissolves into possibility. Night stretches over the world, and above you the sky is a tapestry of ancient light. Each star, each subtle haze, is a messenger from a different chapter of the universe's unfurling story. As you lie quietly and listen, your mind becomes a gentle vessel, drifting through the corridors of time. Tonight, we journey together along the arrow of time, seeking out the tools and methods by which humanity has learned to decipher the past, to read the fossilized memory of the cosmos, and to probe the subtle, shifting rules that have governed its evolution. The search for the universe's memory begins with light, the most ancient of witnesses. For in its endless travel, light carries with it the imprint of the moments it has seen. Across the velvet expanse of the night, the glow of the stars reaches your eyes not as they are, but as they were, years, centuries, even millennia ago. The further we gaze, the deeper we peer into history. But the truest relic of the universe's infancy is not contained in the bright pinpricks of stars, but in a faint, all-pervading whisper of energy, the cosmic microwave background, or CMB. It was in the middle of the 20th century that this whisper first made itself known to human ears. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, tuning an antenna for satellite communications. They encountered a faint, persistent hiss, a murmur that nothing seemed to silence, not the careful cleaning of pigeon droppings from the antenna, nor the meticulous exclusion of terrestrial signals. It was everywhere, omnipresent and inexplicable by any known source. Unbeknownst to them, they had stumbled upon the afterglow of creation itself, the cooled remnant of the primordial fireball, the universe's birth cry, still echoing through space and time. The cosmic microwave background is the oldest light we can see, a fossilized snapshot of the universe as it was roughly 380,000 years after the Big Bang. Before this epoch, the cosmos was an opaque, seething plasma, electrons and protons so energetic that photons could not travel far before being scattered. But as expansion cooled the universe, atoms formed and space became transparent. The light released in this moment has been traveling ever since, stretched by the expansion of space from searing visible and ultraviolet wavelengths down to the microwaves that bathe the universe today. To scientists, the CMB is a time machine. By mapping its subtle temperature fluctuations, they unlock clues about the universe's earliest structure, tiny variations in density that would one day seed galaxies and clusters. Satellites like COBE, WMAP and Planck have charted this ancient light with astonishing precision, revealing a tapestry mottled with minute warm and cool spots. Each fluctuation encodes the primordial physics, the relative strengths of gravity, electromagnetism, and the nuclear forces, the density of matter and dark energy, the fingerprints of quantum fluctuations inflated to cosmic scales. But the cosmic microwave background is more than a relic. It is a testbed for the laws of nature as they once were. By comparing its properties to theoretical models, scientists probe whether the laws we know today, constants like the speed of light, the strength of gravity, or the ratios of fundamental particles, were truly constant, or if, in the furnace of the early universe, they danced to a subtly different tune. Thus far, the evidence whispers of remarkable consistency. Yet each new observation tightens the constraints, narrowing the window in which time's arrow might have bent the rules. Beyond the CMB, the universe's history is written in the light of distant galaxies, nebulae, and quasars. Astronomers train their telescopes on the farthest reaches, gathering photons that have journeyed across billions of years. In these faint signals lie the stories of cosmic evolution, how stars first ignited, how galaxies swirled into being, how the elements themselves were forged in the bellies of suns and in the violence of supernovae. One of the most elegant tools in this pursuit is spectroscopy, the art of splitting light into its constituent colors, a cosmic fingerprint for every element and molecule. Each atom absorbs and emits light at precise wavelengths, dictated by the arrangement of its electrons and the laws of quantum electrodynamics. When astronomers examine the rainbow spectrum of a distant galaxy, they see the telltale lines of hydrogen, helium, oxygen, carbon, each a barcode, each a message from the past. Spectroscopy does more than reveal composition. It tells us how fast objects move, whether they are racing toward us or fleeing away, by the stretching or compression of their spectral lines, a phenomenon known as the Doppler effect. Most galaxies, as Edwin Hubble discovered, are receding from us, their light shifted to longer, redder wavelengths. This redshift is not merely a measure of speed, but a direct chronicle of cosmic expansion. The farther away a galaxy, the higher its redshift, and the longer its light has traveled. By measuring redshifts across the sky, astronomers reconstruct a moving picture of the universe's growth, tracing the arrow of time back to its origin. Still, there are deeper relics to be found. Some of the most profound insights into the laws of nature come not from the vastness of space, but from the smallest scales, in the controlled cathedrals of human ingenuity known as particle colliders. Here, in the tunnels of CERN's Large Hadron Collider and its kin, scientists do not merely observe the universe, they recreate its earliest moments. Within these colossal rings, protons are accelerated to velocities just shy of the speed of light, then slammed together with immense energy. For an instant, the energy of the collision is concentrated into a tiny volume, reaching temperatures and densities that have not existed since the universe was fractions of a second old. In the aftermath, an explosion of exotic particles bursts forth, short-lived quarks, gluons, leptons, and bosons, each a fleeting echo of primordial physics. By sifting through the debris of trillions of such collisions, physicists reconstruct the behaviors of fundamental forces at energies far beyond those found in the everyday world. It was in such experiments that the Higgs boson, long theorized as the giver of mass, was finally glimpsed, a keystone in the standard model of particle physics. But the quest does not end there. Each measurement, each rare decay, is a test. Do the laws behave as we expect, or do they hint at something new, something that might have shaped the cosmos in its fiery youth? Colliders offer a unique way to probe the symmetry of physical laws across time. Some laws, such as the conservation of energy or electric charge, appear inviolate. Others are more subtle, involving the interplay of matter and antimatter, of parity and time reversal. The violation of certain symmetries, observed in the decays of strange and beauty quarks, suggests that the universe subtly distinguishes between past and future, between left and right. These tiny asymmetries, measured with exquisite precision in detectors deep underground, may hold the secret to why the universe today is filled with matter and not its mirror image. Yet the laboratory is but one theatre of discovery. Nature herself has staged experiments on scales far beyond human construction. Cosmic rays, born in the hearts of distant galaxies, or the shock waves of supernovae, rain down upon the Earth with energies that dwarf those of our mightiest machines. When one of these particles strikes the atmosphere, it creates a cascade of secondary particles, a fleeting storm that can be captured by vast arrays of detectors spread across high mountain plateaus. By analyzing the energies and compositions of these cosmic messengers, scientists probe the behavior of physical laws under the most extreme conditions. They search for hints of new particles, for deviations from expected patterns, for footprints of unknown physics. Some seek out neutrinos, those elusive, almost massless ghosts that stream through rock and earth as if it were air. Special observatories, like the colossal ice cube detector buried beneath the Antarctic ice, wait patiently for the rare flashes of light produced when a neutrino interacts, a silent witness to cataclysms billions of light-years away. Astronomical observations also allow us to test the universality of fundamental constants. By comparing the spectra of distant quasars, beacons powered by supermassive black holes, to those of nearby atoms, scientists can measure whether the fine structure constant, a number that governs the strength of electromagnetism, has changed over billions of years. So far, the evidence is consistent with constancy, but the quest continues, ever more precise, ever more sensitive, as if the universe might reveal a secret in some forgotten corner. There are even more delicate ways in which nature's rules might have shifted. The fossil record of stars, preserved in the oldest white dwarfs and neutron stars, encodes the values of nuclear reaction rates long ago. By modeling the cooling of these ancient remnants, astrophysicists infer whether the laws of quantum mechanics and general relativity have held steady over cosmic time. The consistency of stellar evolution, the predictable rhythm of supernova explosions, all speak to the enduring character of physical law. And yet, for all its constancy, the universe is a laboratory of change. The very expansion of space, the birth and death of stars, the coalescing of galaxies, these are all experiments, each governed by the laws of physics, each a test of their universality. In gravitational wave observatories, scientists listen for the ripples in space-time caused by the collision of black holes and neutron stars. These waves, traversing the cosmos unimpeded, carry with them information about gravity in its most extreme form. By comparing their arrival times and patterns with the predictions of Einstein's theories, physicists probe the fabric of reality itself, searching for cracks or deviations that might hint at new principles. Throughout this grand enterprise, ingenuity is humanity's constant companion. Scientists devise ever more sensitive detectors, shielded from earthly noise in deep underground caverns or lofted high above the atmosphere on balloons and satellites. They build telescopes that see not only visible light, but also infrared, ultraviolet, X-rays, and gamma rays, each revealing a different facet of the universe's history. They create quantum sensors capable of detecting the faintest flicker of energy, the faintest shift in a particle's spin, all in the service of peering further back, reaching closer to the beginning. And as each new instrument opens another window onto the past, the story grows richer, more intricate. The universe reveals itself not as a static edifice, but as a living, evolving tapestry, its laws both steadfast and subtle, its history etched in photons, particles, and waves. The arrow of time, that mysterious vector along which past becomes present and present becomes future, is traced not only by memory and decay, but by the very structure of the cosmos. Yet for all our tools, for all our cleverness, there remain mysteries unresolved, questions whispered in the silent spaces between the stars. Are there hidden dimensions or forces that shaped the early universe, now diluted and faint? Did the constants of nature truly never waver, or is there some ancient epoch where time ran differently, where the rules were not as we know them? Each experiment, each observation is both an answer and an invitation, a step along a path that stretches forward, always deeper into the unknown. And so, as you drift at the edge of sleep, let your mind wander through this gallery of cosmic memory, the afterglow of the Big Bang shimmering in microwaves, the ghostly tracks of particles born in colliders and cosmic rays, the spectral signatures of ancient stars, the gravitational ripples from distant cataclysms. All these are the language in which the universe recalls its own story, the clues by which we, restless and curious, seek to understand not only what the laws of nature are, but how they have come to be. In the hush of night, as the stars keep their silent watch, the arrow of time points onward, and the next chapter awaits, hidden just beyond the horizon of our knowledge. There is a hush in the cosmos, a silence more profound than the absence of sound, as if every particle, every wave, every stretch of space were caught in a suspended moment of contemplation. The universe, vast and veiled in mystery, is not a static edifice, but a living poem, written and rewritten in the restless ink of time. If the laws that govern it, the silent rules that undergird the dance of galaxies and the flicker of atoms, are mutable, then what truly is reality? What does it mean to be, to know, to hope, when the ground beneath our reason may quietly shift while we are not looking? Let us float for a while in this trembling and exhilarating uncertainty. For centuries, humanity has sought comfort in the conviction that the universe is governed by immutable laws, gravity, electromagnetism, the strong and weak nuclear forces. These pillars, measured and mapped, have given us the illusion of permanence, a scaffolding for our hopes, our sciences, and our dreams. Yet all along, the possibility has lingered at the edge of our understanding. What if these very laws are themselves contingent, their values and forms not eternal, but evolving, perhaps even capricious? The mind reels at the implications. If the gravitational constant, for example, were to drift over eons, the orbits of planets would become unstable, the tides would wander, and the delicate balance that permits life on our blue world could unravel. Were the speed of light to waver, the very structure of causality, the chain of effect and consequence, might blur. If the strength of the strong force, which binds protons and neutrons in the heart of every atom, were to subtly weaken, stars would sputter and fail, and chemistry itself would dissolve into chaos. But these are the grand, physical consequences. Let us turn our gaze inward, to the interior landscape of the human mind, and consider how the mutability of physical law might ripple through our sense of self and place. We have always yearned for constancy, seeking in the stars, the stones, and the scriptures some sign of order that endures. The intuition runs deep. There must be something beneath the surface flux, something that abides. In this we are not so different from the ancient philosophers who imagined an unchanging realm of ideals, a platonic heaven of forms, or from the physicists who, more recently, have sought a final theory of everything, a single equation from which all else flows. If, however, the universe is itself an unfinished symphony, its score revising as it plays, then we find ourselves adrift upon a sea of possibility far vaster than we had guessed. We must abandon the notion of ultimate, timeless truth, at least in the sense of fixed cosmic rules. Instead, truth becomes a moving target, a melody that modulates, a pattern whose meaning is found not in stasis, but in transformation. This realization can feel at first like a loss, the shattering of certainty, the end of easy answers. But it is also a liberation, an invitation to wonder. If the universe changes, then so too can we. our understanding, our creativity, our capacity for adaptation become not just necessary, but natural, woven into the very fabric of existence. Philosophers have long pondered the question, what is the nature of reality? Is there an objective world out there, waiting to be discovered? Or is reality in some sense co-created by our perceptions, our measurements, our theories? In a universe of changing laws, this question acquires new resonance. Suppose for a moment that the rules by which reality operates are not only hidden but mutable, changing just beyond the reach of our most precise instruments. Each time we measure, we catch only a fleeting glimpse, a shadow of a deeper, shifting truth. Science becomes a dialogue with the unpredictable, a dance of hypotheses that must ever adapt, ever refine. This is not to say that knowledge is unattainable or that reality is wholly arbitrary. Rather, it suggests that knowledge is always provisional, always contingent upon context and time. Our theories are maps, useful but incomplete, charting territories that themselves may shift as we walk them. The search for understanding becomes not a quest for finality, but an open-ended journey, a way of being in relation to the unknown. In this light, even the most fundamental constants, Planck's h, the gravitational g, the fine structure constant, are no longer seen as eternal fixtures, but as characters in a story still unfolding. They are the notes of a cosmic melody, sometimes recurring, sometimes improvising, woven together by rules that are themselves evolving. And we, the listeners and the players both, are invited to take part in the unfolding music. This perhaps is the most profound implication of a mutable universe. It calls us to humility, to curiosity, to openness. If the ground is always shifting, then our wisdom lies not in clinging to what we think we know, but in learning to move, to adapt, to listen for the new harmonies as they arise. Imagine the future of human inquiry in such a universe. The sciences, far from collapsing in despair, might become even more vibrant, more creative, more attuned to nuance. The project of measurement would be like tracking the migration of birds across a changing sky, requiring not only precision but sensitivity to patterns and anomalies, to the subtle hints of transformation. Perhaps new fields of study would arise, cosmological history, dedicated to reconstructing the chronicle of shifting laws, or metaphysics in the literal sense, a science of the evolution of the laws themselves, mapping the landscape of possibility and tracing its paths through time. Technology, too, would become an art of adaptation. Devices and systems might have to recalibrate themselves, not just to local conditions, but to the underlying physics as it slowly drifts. Engines designed to harness the laws of today might need to be rebuilt for the rules of tomorrow. Medicine, architecture, communication, every aspect of civilization would be woven into a dance with the mutable cosmos, a continual process of learning, adjusting, and reimagining. And what of meaning, of purpose? In a universe where all is in flux, does anything endure? The answer, perhaps, is paradoxical. When change is the only constant, the meaning of life is not found in permanence, but in participation. We are not observers standing outside the flow, but actors within it, co-creators of reality's unfolding. Our stories, our art, our love, our struggles, these become not footnotes to an indifferent cosmos, but intricate threads in the great tapestry of change. The night sky has always inspired both awe and humility. For tens of thousands of years, our ancestors looked up and found guidance in the stars, constellations fixed in their courses, a calendar for planting and harvest, a map for journeys across unknown lands. The heavens seemed a realm of order, aloof from the tumult of earthly life. Yet if the laws that shape the stars themselves are evolving, then even the sky is a story in motion. The constellations we see are but a fleeting arrangement, a momentary pattern in the long life of the cosmos. The atoms in our bodies, forged in ancient stars, are themselves the product of changing rules. of forces that may once have flowed with different strengths, of constants that may have sung in other keys. We are, in a sense, children of change, born from the restless creativity of a universe that never stands still. This perspective invites a new kind of reverence. No longer do we seek certainty in unchanging laws, but in the grandeur of becoming, in the beauty of emergence. The universe is not a clockwork wound at the beginning of time, but a living symphony, its harmonies swelling and fading, sometimes familiar, sometimes strange. We may feel small in the face of such immensity, but we are also privileged to witness, to wonder, to participate in the great unfolding. Each moment is unique, unrepeatable, a note in the music of time. If, one distant day, we learn that the laws of physics have indeed changed, or are changing even now, how might that shape our place in the cosmos? Would we feel less secure or more alive? Would we perhaps come to cherish the fleeting beauty of each era, each configuration of possibility? Perhaps we would develop a new philosophy, a wisdom of impermanence. We might learn to listen, not just for the patterns that endure, but for the subtle signs of transformation, the soft shifting of the cosmic wind, the quiet recalibration of nature's rules. We might come to see ourselves not as masters of a fixed order, but as partners in a creative dialogue, learning and growing with the universe itself. The mutable symphony of the universe calls forth in us a humility, a willingness to surrender our need for final answers. Yet it also calls forth courage, a readiness to face the unknown, to imagine new possibilities, to find meaning not despite change, but because of it. In this light, the universe is both less and more than we once dreamed. It is less a machine, more a mystery, less a fortress of certainty, more a garden of becoming. Its beauty is not in the perfection of its laws, but in their capacity to surprise, to evolve, to give rise to new forms of order and wonder. As night deepens and the world grows quiet, let your thoughts drift upon the currents of possibility. Somewhere, far beyond the reach of our eyes, perhaps the fabric of reality is shifting, the rules being rewritten in the silence of the void. Or perhaps, here and now, the constants we take for granted are whispering their secrets, changing in ways too subtle for us yet to hear. We, the dreamers and the doers, find ourselves poised between knowledge and mystery, certainty and change. Our questions are lanterns, casting light upon the darkness, even as the path ahead twists and turns in unexpected ways. The universe may not owe us answers, but it offers in abundance the gift of wonder, the invitation to explore, to question, to listen for the hidden music that weaves through all things. And so we rest, not at the end of certainty, but at the threshold of infinite becoming. The mutable symphony plays on, and in its unfolding we find our place, not as distant, passive witnesses, but as vital notes in the song of change, forever listening, forever learning, forever becoming. As our journey through the shifting whispers of physical laws drifts to a close, we float gently like a comet tail fading into the hush of space. Let your mind rest among these cosmic mysteries, and when the night calls again, return with me for more Dreamtime tales that shimmer just beyond the stars.